Okay, so how was the quiz? Is everybody back? Yeah, so obviously, right, I'll take a look at it and try to sort of grade it when you guys sort of all submit it. Exactly, right? It all comes down to practice, right? What you should be aware of, obviously, is that the course requires you to obviously keep pace with the material, okay? And the only way to master, right, the information is to keep on practicing. And the breadth of exposure that you can get from doing the practice problems, problem sets, right, is important, okay? A single quiz is not going to harm you, but obviously, right, you want to make sure that if you have a pattern of not doing one of the quizzes, then obviously that's obviously of concern. Okay. So, anyways, I will take a look at it later, and I'll get them graded, and then I'll get sort of your marks posted onto D2L as well. But are there any questions on sort of how we administer the quizzes? Is everybody okay with the format? Are there any concerns in terms of time? Yeah, okay. Yeah, so there is a likelihood, right, that even the fall offering of the courses, like the fall 2020, everything will be online as well, right? So I think that it's more and more looking like that is the case, particularly with more and more institutions saying that more primarily all courses in the fall for post-secondary will be offered online. Okay, so there's a possibility of that. We need to continuing to sort of not perfect it, but make it better, right? In terms of sort of the experience for both the students, okay, as well as obviously for faculty. Right. I agree with you. So I think online learning is not for everybody, right? There are many restrictions as to what can be done with online learning. But you know what? You just have to, unfortunately, given this is a once in 100 years type of pandemic, right? So we just have to make the best of what we can, right? Given the limitations of what we can do online and the level of interaction. Okay. Okay. Shall we continue with the material? Unless, does anybody have any questions? I'd like to sort of continue with the material if possible. Rana, are you back? Rana, I cannot hear you at all. Yes, so just I actually enjoy teaching the course in person as well. I feel that every time I'm doing something online, I'm just simply I see. So Rana, what you can do is maybe you can sort of leave the audio and rejoin the audio. So Zishan, I'll very quickly answer your question on that. So the idea is that the FCC governs. So the FCC is the federal commission that actually deals with communications. In fact, governs all of the powers and minimum distances of any cell phone towers. Okay, so there is never a link in terms of long-term exposure. Okay, so you should be aware of that. Okay, but nonetheless, so there are standards that governs everything, right? Obviously, from a health perspective, in terms of the power that each of these cell phone towers can transmit, and so on and so forth. So there is guidelines for ensuring that no harm is done to the human.
I think I'm good now.
Yes. Okay. Good. I can hear you. That's good. Okay. Yeah. So Bongo's a little weird. Sometimes I have that problem. Sometimes if you change sort of your audio input, for some reason the audio is not connected, and I've experienced that. So what I usually do is not leave the session, but I just reconnect the audio, and then I just do that microphone test again, and then it seems to work fine. Okay, Rana.
Okay. Thank you.
Okay, let's get going. Any questions? I think you might be talking, because when someone talks, the icon blinks, but I couldn't hear you at all. So
I wasn't talking. That's the problem. I see it blinking. It's just I wasn't talking.
Oh, I see. Okay, interesting. Okay, but okay. So, any questions at all before I sort of get going?
All good.
Okay, so I want to sort of get on with the material first, right? I want to get hopefully through this deck of slides for now, right? So that we can take a break after that. And then I will come back and I want to spend some time on assignment 1. But I need to go through sort of the signal decomposition in essence with you first, right? Before we can actually do that. Okay, so when you set it up, so you'll notice that I effectively, intentionally, I should say, make the due date of assignment 1 the following Monday after next class, right? So what I want is that I want you to be able to ask some questions also next class before it's actually due. Does that make sense? Okay, so I want you to take an attempt. So after today's lecture, you should be able to do the assignment, right? There's one thing that I want to go through with you, which is section 3.6 later today. And when we can get through that, then you can actually start working on the assignment. But I'm intentionally making it due on the Monday after next week's lecture so that we can spend some time next lecture if there are any questions to address your concerns. Okay? Okay, so let's move on with the material here, right? So all that we have seen so far, right, is what we call the time domain plots. It's simply very simple. It just says this, right? If we have a sine wave, a time domain plot just simply says that with respect to time, which means that your x-axis, right, is the time axis. Okay, what does that mean? It means that now I'm observing the behavior of this sine wave, right, as time changes, which means there's incremental time going, right, and therefore the wave goes up and down, up and down. Okay, what do you think is wrong with this, or can you see of any disadvantage of viewing the sine wave in a time domain plot? Because I want to introduce you to a new sort of vantage point, which is to view the same plot, but now instead of having time in the x-axis, I'm going to have frequency in the x-axis. But why?
This sine wave shows only one amplitude, whereas sometimes if I have different amplitudes, I'll have to draw another one.
That's right.
Is that a problem?
Yeah. So that itself is not a problem. Okay, but there is a issue with the fact that number one, right, is that if this is a periodic signal, right? True. The sine wave is a periodic signal. In fact, there's a lot of redundant information in this plot. Do you agree? I mean, if time were to go to infinity, right, what I have is really, right, a signal that's periodic that I know repeats itself. And what I have here is nothing but redundancy, because I only really need one cycle if I know that it's actually a periodic signal. So there is a redundant information is one thing. Okay. Maybe I can condense that a little bit, right? So you guys just drew a sine wave. Some of you may find it very awkward to draw one, right? But if imagine you have to draw this and you have to draw that continuously for infinite amount of time. Okay, so there's a lot of redundant information associated with it. So that's the first. But the second one is what Rana just said. Now, most signals that we get are non-simple sine waves. Remember, right? Like the example I gave you was like the orchestra, right? And in the event of the orchestra, well, there are many tones coming towards me, right? So if I was to start overlaying multiple time domain plots, which means I'm going to draw another sine wave, right, of another amplitude over this guy. 2 waves are probably fine. But the moment I get to 5 waves or 10 waves or 20 waves, well, essentially what happens is that, does everybody see that this time domain plot will get very cluttered? Which means that you're overlaying all of these simple waves on top of each other, which at some point in time, you cannot actually see the independent waves anymore. Okay? So the frequency domain plot, right, that I want to introduce to you is not trying to represent the information, like trying to change the information, but it's simply only trying to represent the information from a different vantage point, which means from a different visual, right? An example of which, right, is this, is that if I now have the x-axis to be frequency. Okay? I'm still preserving. Remember, there are 3 characteristics associated, right, with the sine wave. Does anybody remember what the 3 are? And you can type in the chat section. I'm just trying to make this a little bit more interactive with you guys, right? So what are the 3 characteristics? Anyone? What are you, right? Exactly. Amplitude, frequency, and phase. By now, you should have that like memorized. It should be really part of you. Okay. For what I can do now is that in fact I can remove a lot of the redundant information here that I see in the time domain plot, because this is the way that it keeps repeating itself. In fact, what's really important for me are just simply the amplitude, frequency, and the phase. Okay. So if I say this, right, I'm going to now have, this is 1, 2, 3, 4, 5, 6 cycles. Right? So this frequency of 6. Then at 6, I'm going to draw the corresponding amplitude, and the peak amplitude is 5. So it's 5, 6. Does everybody follow? But I do lose an information that I did not capture in the frequency domain plot. And obviously, that's the phase. Because the phase, right, is by definition, respect to time equals to 0. And I've effectively removed the time element from this vantage point. But nonetheless, there is still many benefits of having the frequency domain plot, as we'll see later. Because the one thing that I want to sort of get onto is the definition of what's called frequency for you guys. Okay, so if we take a look at this, right, what we have is we've effectively translated this image, right, the time domain plot, into a frequency domain plot while preserving 2 of the components, the frequency and the peak amplitude. This allows me, right, to capture the essence of the sine wave, less, of course, the phase. And its implications comes, right, because most of the time we do not transmit single tones. Right? But rather, we transmit multiple singletons. So if I now say this, right, there are 3 simple waves here. Does everybody see that? The blue, the black, and then the red. Okay. What do you think the frequency domain plot will look like for this particular diagram? First of all, right, if we say that one simple wave results in a single spike in the frequency domain plot, what do you think, without going to the details of the values, right? What do you think the frequency domain, corresponding frequency domain plot of this diagram will look like? Someone? Anyone? Three spikes. Okay, effectively that's what it is. Okay, so then if we know that this is what it's going to like, does everybody see, at least visually, right, that the diagram on the right, it's much easier visually than the diagram on the left, right? And you can imagine, right, if there's 100 simple waves that make up this composite signal, then this image here will be extremely cluttered. But this diagram here shows me a couple of things: the frequency of each simple wave and the amplitude of these simple waves. So let's go through them one at a time, right? So let's start with the lowest amplitude one, which is the 5 volts, right? So I have a black spike here, which is at 5 volts. And because this is 1 second, there are 16 peaks, frequency of 16. There's the blue sort of wave here, right? Peak amplitude of 10, right? 8 peaks, right? Which is really half of 16, 8, 10. So why is this red line here 0, 15? What does it mean doesn't spike? William, can you expand on that a little bit? Why is it 0, 15? Is this a sine wave? Is this line here a sine wave? Exactly. Okay. So it is actually still a sine wave. It's just that the peak amplitude is actually 0. Sorry, the frequency is 0. Sorry. So what we capture ultimately, right, is that there is a frequency of 0, but still, right, with a voltage of 15. What do we usually call this? Does anybody know that there is DC versus AC? Like in terms of the batteries, the dry cells that you use, they're usually DC, direct current, versus alternating current, which is what you get at home. Right, and alternating current, as I said, is really a current that comes in as a sine wave, right? Whereas in DC, right, this is a flat line. Okay. Any questions on sort of the time domain versus frequency domain? So obviously, right, what do I need you to be able to do? I need you to be able to convert interchangeably between the time domain plot and then the frequency domain plot. Right? So a hint for your quiz next week, right? It is important that you're able to transform given a time domain plot into a frequency domain plot, and it's important for you to, given a frequency domain plot, right, be able to transform back to a time domain plot. Okay? Any questions? Same frequency, but different. Oh, it'll be 2 spikes at the same frequency point. Right? So essentially, what that will mean that there will be 2 spikes. So in this, oops, pen, give me a pen here. Right? So in this frequency domain plot, right, where this is F, right, you're going to have obviously 1 spike. Let's say at frequency F, right? You're going to have 1 spike. And then obviously you could have a second spike, right, at a different amplitude. So this is the peak amplitude, and then this is the peak amplitude for the other guy. Okay. Okay. So now let's take a look at composite signals. Okay, because this is where the signal decomposition comes in. Okay, so first of all, you know that this is a composite signal, right? Because obviously there is different peaks. It's not a sine wave, right? It's not a simple sine wave. Essentially, that's what it is. Okay. Second of all, right, you should be able to recognize that this is in fact a periodic signal because this is a pattern that keeps repeating itself. In fact, there are 3 cycles of this composite signal. Okay. But the challenge now is this, right? And anybody can chime into this. How many simple waves do you think there exists that makes up this composite signal? Take a look at it. And I'm not asking for a scientific, I'm just saying visually, right? How do you think this composite signal was created? And how many simple waves are there that mix up to it? Anyone? Two? 3? How? Why? So they're all along the same lines, and it's actually interesting that there are differences of opinions, obviously, because you're trying to decompose it visually, right? But think about this, right? If you notice and you zoom in a little bit, this peak here is a little lower than these peaks here. Does everybody see that? Right? This peak here is different from this peak here. Okay, so without being too scientific, I can show you what the decomposition of it is. And I said this, right? There's no real right answer because obviously, right, you're trying to decompose this visually. Okay. The idea is this, is that if I now have this as a composite signal, right, it is likely for me to say this, right? In the time domain plot, I'm very likely going to have this big wave here, right? So these are the simple waves. So this is what I mean by signal decomposition, right? I take this sort of signal here, and I can see that, oh, there's a fundamental sine wave that goes up and down, up and down, up and down, which is this guy here. We call that the fundamental, but we'll talk about that later. There is likely a second wave here, right? Sort of along the lines of what Yongju and actually they're both Yongjus, just spelled a little differently. So Yongju 1 and Yongju 2. Okay, that allows for this little peaks here on the sides. But because, right, if you notice, and maybe some of you did not, right, is that there is a lower peak here. Obviously, that likely is a third signal that says this, okay, well, this signal here is compensated by an addition of this signal, right? So there's a dip, but then there's an increment here. So there's a slight lower value here as compared to the two sort of years, right, on top of the sine wave. Does everybody see that? Rana, are you there?
Yes, I'm there. I'm actually
Okay,
trying to figure it out. I'm looking closely at it.
Right, exactly. Okay. So what I have is, again, I've said this is non-scientific, right? And I'm just doing it in a very crude way because I want to show you what signal decomposition really is, and I'll show you what it means to do it sort of by trigonometry by using trig identities. Okay, so the idea behind this is very simple, right? Is that if I have a composite signal here that I have here, I know that they're made up of simple waves, right? And my goal obviously is to determine what the simple waves that makes up of it, right? And the way to verify obviously is that if you now add up time-wise of all of these three simple waves, then you should get this composite signal. And that's what it is, aggregation in time. So think about this, right? Is that if you go to an orchestra, you have a tone at a very low frequency of a very high amplitude. So it might be a tone like this, right? And then I have a slightly lower amplitude, but a higher frequency tone, right? That goes, right? So, and then I'm not a, I don't sing at all actually. And then you have another third sort of frequency that's even higher frequency, but even lower amplitude, right? And that's sort of the tones that are being played by the instruments. But what your ear hears, right, is actually this. So I could do it. I usually do an experiment of this in class actually. So I have Chantel and Alan and Rana, true?
Yes.
Right, that are on their mics here. Okay, are you guys comfortable unmuting yourself, Alan and Chantel and sort of Rana?
Well, I'm already unmuted, so.
Yeah, so I'm getting it too. Okay, so can I have Rana produce a low tone? Just hold a tone. Can I have Chantel do a tone as well, but a slightly higher frequency, so high slightly pitch? Can they do it both at the same time? Right, and if Alan is willing, right, can you do something even higher? Alan? I know he has
Alan
a mic.
is not willing to participate in this.
Come on.
No.
Let's do it, yeah.
Okay, Alan, can you do the lowest tone then? So obviously we'll let females
I can do the higher one. Yeah, I can do the higher one.
That's right, exactly. Okay, so Alan, can you unmute yourself and do a very low tone? The lowest tone you can do, and hold it for 10 minutes.
10 minutes.
No.
10 minutes?
No. Just for demonstration purposes. Can we do a very low tone? Let's go, Alan. Chantel. No, hold your tone, Alan. Chantel, and then obviously Rana. Okay, thank you, everybody. Okay, so that's great. That's a great demonstration. Thank you, everybody. Okay, so everybody should give everybody a round of applause, right, for being sort of a. So you see that, right? That's actually the three simple waves. Everybody was producing a single tone, and the three simple waves actually effectively gave you that harmonic, right? Because that composite signal, right, took different frequency components and added up together. Okay, so essentially that's what signal decomposition is, and in a visual way, right? We went from saying, okay, this guy could be decomposed into two, maybe this guy's going to be decomposed into three, but regardless, right? Let's assume that we know that it's three. Okay, then we can then plot the corresponding frequency domain plot associated with it. Does everybody follow? Okay, then the next question is this: why is this important? Why is this important in the transmission of signals? So let me ask you a question, right? What if the three tones were being produced, but my channel that I'm allowing the signals to go through did not allow the highest tone to go through? what happens? So effectively, I have Alan going through, Chantel going through, but then the channel did not allow Rana's tone to come through. What happens? Did I get a exact replication of the signal?
No.
No, exactly. Okay, this is what we call bandwidth required, right? So this is the signal bandwidth that's required. Effectively, right, and I'll define this formally for you later, okay, is that for me to accurately reproduce this composite signal, I would need to have all these three components to be transmitted, okay? And what we then have, right, is that we have three different spikes, okay? And because it's a periodic signal, right, I'm going to sort of give you one theorem that you should know, okay? And it's that the frequency decomposition of a periodic signal, right, is represented by spikes in the frequency domain, because each spike represents a periodic single tone, or a periodic simple wave, as was shown, right, in a couple of slides earlier here. Oh, not this one, but this one, right? Every single frequency shall result in one spike. Okay, so if the composite signal is periodic, then the frequency decomposition of this periodic signal, right, will be represented by spikes. Think on that for a minute. Okay, think on that for a minute. Does it make sense? Because the question is this, right? As I said, spikes in the frequency domain just means that the wave itself was periodic. True? It was a single tone, a specific amplitude, a specific phase, and a specific frequency. Now, let me ask you a question. Can the composite signal be periodic if any of the simple waves is non-periodic? Anyone? Let me ask the question again. Can the composite signal, which is the aggregation of the simple tones, still be periodic if any of the simple waves are not periodic?
No.
No. Does everybody get that? Let's assume I say this, okay? Alan, I want you to make a tone, okay? Not anymore. Chantal, I want you to make a tone. So they go ba, ba, right? Then they hold the two tones together. And then we have Rana that comes in that's not making a tone that's periodic, but making a signal that's non-periodic. Can the aggregate of that still remain periodic? And the answer, obviously, as Rana said, is no. Right? So by definition, right, we say this, is that if we have a periodic composite signal, the decomposition of that, right, into the frequency domain will show that it's a plot, right, that is composed of spikes, because every single simple wave that makes up to the composite is actually a spike. Okay, and for those that are interested in digital signal processing, right, we have specific terminologies for each of these. The lowest frequency component, right, we call that the fundamental frequency, right? The one that's 3 times or 9 times, we call that harmonic, specifically, right, the third harmonic and the ninth harmonic, because this is 3 times the frequency of the fundamental, and this is 9 times the frequency of the fundament.
Can I ask a question?
Yes, of course.
My connection got cut off when you were explaining the frequency 3 and frequency 9. Is it possible to repeat that, please?
The 3.
The blue wave, the frequency of 3 hertz, and the black wave, the frequency of 9.
Okay. Yeah. So I said that these are just multiples in terms of the base wave. The base wave here, the fundamental, the one with the lowest frequency, right,
Yes.
is oscillating at frequency f. You may have heard of the terms harmonics in music. Harmonics are nothing whereby there are different tones that are at multiples of frequencies from the fundamental. So in this case, right, this blue one is oscillating 3 times as fast as the red wave, and the black wave is oscillating at 9 times the red wave. So we call this respectively the third harmonic and this the ninth harmonic.
Okay, and those blue and black wave, the frequency of them, was that deduced from the drawing above, the one with all these waves?
That's right. Yes.
How so? Can you show me, please?
No, we cannot do that. I'm unable to do that visually. I'm saying that this is the best guess of what we think the reproduction is. And the formal way to do it is actually using trig identities decomposition. And I'll show you that later because that's part of your assignment 1. So as I said in the assignment, there is a visual that you do, which is obviously a best effort analysis of it, right? Because it could have been composed of 7 waves, for all we know, for this composite signal, right? If we just look at it visually, okay? But what we can show mathematically, and that's why we have an exercise on trig identity decomposition, is that it will give you precisely how many simple ways that actually exist. So this is a very crude ballpark estimate, and the formal way, right, which the book doesn't go into at all, but I give you to you as an assignment because I want to expose you to that, right, is to do it by decomposition by trig identities. Is that clear, Rana?
Yes.
There's no proof for this at all, which in fact, this is our best estimate of it.
So I'll say this is an assumption.
It's an assumption, exactly. It's a best guess. It's not even an assumption. It's a best effort guess of what the simple waves are that makes up of this composite signal, because I know there's a big wave here, there's some peaks, and there's a lower peak in the middle. And the way I could come up with a diagram of this sort, right, if I add up in time, is these 3 waves. But there could be other ways of achieving the same composite signal, right? But I cannot mathematically, I cannot prove that visually. Does that make sense?
Yes.
It's just like if you hear a tone, right, a composite signal as sound, right? Are you able to tell how many tones make up to the composite signal? I mean, some audiophiles can, but some people can't. Do you understand what I'm saying?
Yes.
But I want to show you I want you to be experienced the mathematical approach to that, which is decomposition by trig identities, and that would be a formal way to show that. Okay, but for now, for the purpose of this particular slide, right, the goal is for you to experience, right, the decomposition of this, right, simply, right, through a visual sense, right, and finding out what the corresponding time domain plot is, which is the top diagram here, and the corresponding frequency domain plot. Okay, and then the theorem I want you to get out of, right, is that if it's a periodic signal, the decomposition of this will result in spikes. Because all of the simple ways that make up a composite periodic signal must be periodic in its simple ways. Okay? So what about a signal that's non-periodic like this? This is human voice. What do you think now? If I show you this, right, as a composite signal, what do you think the frequency domain plot would look like? Anyone? Very inconsistent, sure. Right, so that's one way to describe it, right? So this is like a human voice, right? If you were recording my voice print as I'm talking, right, this is what you get. If you talk to Siri now, it will produce that voice print for you. It's capturing the frequencies, it's capturing the amplitudes of the frequencies, right? So what you'll see now is that if it's a non-periodic composite signal, right, what you end up having in the frequency domain plot, right, is that it's actually a continuous curve. Because there is no periodicity to all of the simple waves that are making up to it. Right? In fact, every frequency component can exist in this wave. But there's one very interesting read that you have that wasn't as obvious in the periodic case, is that does everybody see that this is frequency, right? So this is human voice, right? Between 0 and 4 kilohertz. Right? So it will be me going from the lowest tone I can make, like, and I can go up to 4 kilohertz. Okay? But what's interesting is that if you take a look at the y-axis, where this is amplitude, this means that at the very low frequencies, there are very low amplitudes. This also means that at the very high frequencies, there are very low amplitudes. But also tells us that the amplitude is high of the frequencies that are between f, and let's call this 2f. Right? So there's a plateau here. Does that make sense for human voice? Think about the speech that you make. Do you normally emit very low tones and very high tones? Or do you normally emit your middle range of your vocal range? Which means human voice is actually most prominent between 1 and 3 kilohertz. Does everybody get that? Like when you speak, you very unlikely are emitting the very low tones. When you speak, you're also very unlikely to be emitting only the very high tones, but rather the range of tones that you emit in your speech is the middle of the range of your entire vocal range. Obviously, Alan is a different example because Alan only emits in the lower tones. True? Right, exactly. But I'm talking about normal speech, right, Zitang, right? I'm talking about normal speech, right? Usually, right, for most human beings, right, your speech that you emit in tones, right, is very much obviously in the middle range of your tones. Okay? We call this the frequency response of the signal. Who has experienced MP3 before? Who's dealt with MP3s? Anybody here sort of produced MP3 files before? Anyone? Chantel, have you sort of dealt with MP3s? Like, take a audio file and then produce an MP3 from it, like a digital output? Yeah. Okay. Are you guys aware that MP3 is a compressed version? Yes. How do you think MP3 produces a compressed version of the audio stream? How do you think MP3 produces a compressed version of the audio stream? Anyone? Exactly. Okay. It actually, I wouldn't say it's undiscernible. Undiscernible just means that you cannot hear it, right? Which is probably in line with what I'm saying. Is that, in fact, the MP3 compression technique removes the low and the high tones that are low in an amplitude. Which means, right, if I have a musical instrument that's actually playing, for example, okay, and obviously a musical instrument itself has a range of frequency it can actually produce. Now, if very few of the tones that are emitted, right, are at the very high and the low frequency in terms of amplitude, which means that, yes, there are some high and low tones in it, but they're very, very low amplitude, which means that you may not actually be able to hear them along the lines of what Shankai is saying, right? It's undiscernible. We can't hear it, right? Then, in fact, if you do compression by removing those, which is by looking at this spectrum here, right? Effectively, what I'm saying is this: I don't want, in my reproduction in MP3, I want to remove anything that is below a certain amplitude. So I'm removing all of these tones, and I'm removing the high and the low tones because they're not produced much at all. Does it affect the overall quality of the music that you hear? Which means I'm exactly. And that's what MP3 compression is all about, is that if we take a look at the frequency response of the audio stream, which is what it does, is it usually does an analysis of that. And it says this, okay, for me to convert this audio into this, obviously every piece of music is slightly different. I'm going to now remove the very low volume, low amplitude, low and high tones. I can still reproduce the music in general, right? But I do lose some fidelity with it. But the fidelity that I lose doesn't have a major impact on the quality of the reproduction. Does that make sense? And obviously, right, if you start to look at it, right, it's a very ingenious way of actually doing compression, is that I'm taking away the signals that are really not adding much to the quality or the overall experience of the music. And from then on, obviously, right, I'm able to produce a much smaller, or what we call compressed, right, version, right, in terms of file size, right, of the original music. But obviously, right, it would be unacceptable, right, to a lot of audiophiles, right? So they look for lossless compressions and so on and so forth. But MP3 in general, right, that's the technique behind it. Okay, so the big thing I want to get here is this, right? Two theorems that I want you to know, right? First, you should be able to go from a time domain plot to a frequency domain plot, right? Big hint, right? You might see this in your quiz next week. The other thing I want you to be able to recognize is that if I show you a plot, right, of a frequency decomposition of the signal, if the signal itself in its composite form is periodic, then the resulting frequency domain plot shall be spikes. If I show you one of a composite signal that's non-periodic, then the resulting sort of frequency domain plot of that, right, shall be a continuous curve. Okay, so let's take a look at some examples of how we actually deal with this. But I want to formulate now introduce you to the concept of something known as bandwidth, because bandwidth, right, is what we need to deal with. Okay, so the bandwidth by definition is very, very simple, right? Irregardless whether it's a continuous, right, in terms of periodic signal versus a non-periodic signal, the bandwidth that a channel or a signal, I should say a signal requires, is nothing but the f high minus the f low, right? Which means it will be the highest frequency component in that audio piece, and then subtracting away the lowest. This is the range of frequencies I want to be able to transmit, and that's the bandwidth. So in other words, right, you can take a look at the bandwidth of a signal to be the range, right, of frequencies, right, that this signal carries. And what you want is that the channel allows this range of signals to go through, right? So by definition, bandwidth is nothing but f high minus f low, which means in this case, right, is 5,000 minus 1,000. This gives you 4,000. This is a periodic signal because this is spikes. This is a non-periodic signal because this is a continuous curve. And in both cases, the bandwidth is 4,000 because it's f high minus f low. Okay, and that will be our formal definition of bandwidth, f high minus f low, and the units is obviously in hertz. Okay, I should also add, right, in all of your assignments and all of your quizzes, right, as you work through the problems, your final answers must have units, right? If you don't have units for your final answer, then you usually lose 1/4 of a point. Okay, because units matter, right? You don't need to carry units throughout all your computations, but you need to have a unit associated, right, with your final answers. Okay, any questions? Let's do a couple of examples here. Okay, let's say that we have a periodic signal, right? The bandwidth is 20 hertz. Okay, the highest frequency component is 60, right? And it has a frequency and it has a bandwidth 20. What is the lowest frequency? So a couple of things here, right? It's a periodic signal. So in the frequency domain plot, should I see spikes or continuous curve?
Spikes.
Exactly. Okay. If I know that the bandwidth is 20, which means the f high to the f low has a range of 20, and the f high is at 60, what is f low?
40.
Exactly. Right. So this is what I should expect to see, right, in sort of the frequency domain plots. So Yunbin, I'll take a look at what's written in the quizzes. I haven't had a chance to see what everybody has done, right? But if any case, I will, depending on sort of the responses, but everybody going forward, right, you should have final units for your final answer. You should have units for your final answers. Okay, but then again, right, the 1/4 point that is taken off, right, is really inconsequential in your final grade, just so you know. Do you understand what I'm saying? But it's more of an awareness, right, that every final answer, regardless of what you do, right, should always be associated with some kind of a units. Okay, Yunbin. Let's look at another example here. Okay, if there's a periodic signal, right, and it's decomposed into 5 sine waves, and I'm telling you the frequencies of each of these simple waves: 100, 300, 500, 700, 900. What is this bandwidth? How do you determine its bandwidth? Exactly. Same thing, right? It doesn't really matter. It's always f high minus f low. If I say that all of them have a maximum amplitude of 10 volts, so all of these frequency tones are emitted at the same amplitude of 10 volts, the periodic signal should result in spikes or continuous curves.
Could you repeat the question, please?
Yeah, would the frequency domain plot be spikes or continuous curve? It's a periodic signal. There are 5 simple waves associated with it. Would I see spikes in the spectrum, or would I see continuous curves? Spikes, exactly.
Spikes,
how many spikes?
3, 4, 5 spikes.
Exactly. Right? So the bandwidth is 800, right? We should see 5 spikes, and they're all at 10 volts, which means all of these components are at the same equal 10 volts amplitude. Okay. Let's look at another question. Now, it's a non-periodic signal now. Should I see spikes or curve?
Curve.
Exactly. Okay. It has a bandwidth of 200 kilohertz, which means the f high minus f low is 200. I'm telling you now that the middle frequency is 140, right? And it's at 20 volts. And the two extreme frequencies are at 0. First of all, what is F high and what is F low in this problem?
$240 is the high.
And how do you get that?
140 plus 100, because I think the middle is
exactly, precisely.
Yeah.
Right. So the bandwidth is 200. The middle is 140. Right. So 200 divided by 2, you go 100 to the right and you go 100 to the left. Right. So what do you think the frequency domain plot looks like?
a curve from 0.
Yeah, it's a curve.
Yeah, from 0 to 140 and then back.
But does it have to look like this? So what I'm saying is this, right? Is this the only way to draw this? Can I have, correspondingly, can I have something like this, right? So this is at 140. This is at 40. This is at 240, right? And then this is F. And I know that this is at 20 volts, right? So this, right, is at 20 volts. Is this a valid frequency domain plot? Is this valid? I know this is at 20 and this is at 0.
Yes.
Exactly. It's absolutely valid, right? The only specification you were given is that this must be at 20, this must be at 0, and this must be at 0. But this must be at the max, right? So that's what the problem says. But it did not require this to be linear only, right? I could have done any pattern I want as long as I do not exceed 20. Does everybody follow? Yeah.
So could I do something similar to the previous one where the curve goes up slightly and plots for a while and then goes down?
You can draw here.
Oh.
You can use them, yeah.
So something like that, and then keeps here and then goes down.
Exactly. Anything is valid as long as the maximum is at 20 at 140, right? And the two ends are at 0.
Okay.
Okay.
Yeah. Thank you.
No problem. So let's take a look at. Oops. Let's see this. I almost wish that I can have two whiteboards, like a whiteboard on the side with the screen. Okay, so I want to take sort of a quick break here. Is that okay for everybody? And then I want to go into digital signals.
Sounds good.
Okay. Shall we take say a 7-minute break? So we'll go to 11:35.
Okay.
Right. Okay. 7 minutes, right, and then we'll resume, right, 11:35, so everybody can get a bathroom or a coffee break. Okay.
Thank you.
Thank you. So everybody back?
I'm here.
Just wait for a few seconds here. Let me just load up. Are you guys all getting used to online courses already?
Not the best way to learn, but I guess we do what we have to do, right?
Yeah. No, but so the institute actually is looking at options of actually offer like e-learning programs now. So the fact that most courses have pivoted online, I don't know. I personally, for myself, I don't find. I think that there are some courses that are very well suited for sort of e-learning, and there are courses that are not as well suited for e-learning. So that's sort of my take on that. I think that certain courses are better when they're done in person, and I think the impact is higher when it's done actually in person. Right, but obviously that's sort of my opinion on it. So
I think human interaction is very important when it comes to learning.
I agree, because my biggest thing that I have here is that your facial expressions, your everything is blind to me. So in actual class, I pick that up very quickly. So I know that I need to talk about certain concepts a little bit more. I know that some certain concepts are good for you. I think that sort of the real-time, in-person delivery of a lecture is more engaging in many ways. I think it's easy for you to, and I don't know what you guys are doing. Maybe you're watching a video on the side, right? So that's sort of blind to me as well. So my preference, personally, right, it can be more internalized. I think you relate to a concept, place, and time, and exactly, and I think that short-term sort of pivoting online is probably fine, but long-term pivoting online actually I think changes the entire experience. Not that it's not going to be effective, but it's just a very different experience altogether. Okay, so the reason I wanted to take a quick pause. Oops, I thought I loaded up the assignment. Oh yeah, it's here. Okay. I see. So I have to create a second window here. Okay, so I want to just load up the assignment because I think this is a good time to just quickly take a quick look at it. Okay, can you see this?
Do we need to bring it up in our window as well?
No, you don't. I have already shown you on Bongo, right? So I'm not going to go through all of it in detail, right? I just want to give you an outline what you're supposed to do.
Okay.
Okay, so a couple of things, right? As I said, that the assignment, oops, this is too large, is that the assignment is, should have done it in Word, but so the assignment is due not the coming Monday, but the following Monday, which means, right, essentially, right, there is an extra time for you to ask questions next week. So I want you to start making an attempt on the questions. You can do now 3 out of the 4 questions. My hope is that I can get through to the section 3.6 later, so that you can also deal with a question. But if not, we'll cover it next week, and then you will still be able to get it done by Monday. Okay, so it's due the 2 Mondays from now, right, at 5:30. So you have a chance to ask question next week. This one you must submit in a PDF only. Okay, it's very difficult for the marker to receive, hundreds and hundreds of pages, right, where they're all different formats, right? So I want you to find ways of, even if you produce a JPEG, export that to Word or some sort, and then assemble it as a PDF. And there are many other tools that can actually do that, but you must submit a PDF only using for submission for this course. Okay. Obviously, you only allow 1 submission, right? Which means 1 single file, right? 1 submission. Okay. Let's keep in mind, right, that the marker downloads this, right, document by document. Okay, and he's trying to grade through all of the students, right, document. So a consistent submission, right, is probably respectful, right, for what he has to do. Okay, obviously in your submission, I want you to make sure that I said it doesn't have to be a cover page, but you should have your name, student number, and set. A lot of times students submit something and then they forget to write their names, right? Which means it's difficult for you to give a mark because we don't know who it belongs to. Okay, and then obviously this particular quiz, this particular assignment has 4 questions, totally 31 marks. Okay, so let's go through the questions. Okay, oh, where you submit, right, again, is in D2L, right, and then there's an assignment 1 folder that has been created.
Needs to be handwritten as well?
Sorry?
Needs to be handwritten as well?
Yes, handwritten. Okay, handwritten doesn't mean it has to be by hand, but handwritten just means that you can digitize that right on the digitizer.
Yes.
Okay, but it cannot be typed up. Essentially, that's what it says. You cannot type up the solution. Okay. There are a couple of questions. Question one, which is another additional practice on logs, right? A little bit more challenging than the ones you've seen, right? Just because I want you to sort of spend some time to ensure that you can actually do this. They're not difficult, but they're just something that you will grow, and more practice means more expertise. Okay, so there are two questions on that. One in sort of computing the value of x, one obviously to do it symbolically. Now, this is the fun question here. Does everybody see question 3 here?
Yes.
Okay, this is the question where I say this. You know what? I'm going to give you now a composite signal, right? And this is a composite signal because obviously it's not simply just sine, a sine 2 pi ft plus theta. But I've given you a signal that I purposefully, right, put together, right, in an obscure form for you. And my question and challenge to you is this: is that can you decompose this into its simple ways? So in the previous lecture material that we showed, right, we did it visually, but I don't want you to do that now, because obviously that's not a unique solution that we produce. What I want you to do now, right, is to a very sort of systematic way, decompose this using trig identities. So if you recall what trig identities are, there are things like sine squared plus cos squared equals to 1. Do you remember that? It could be from decades ago, it could be from years ago, it could be from a lifetime ago, right? But it's essentially just sine squared plus cos squared equals 1, and many other identities as well. So then there are no restrictions, right, in the identities that you can use. But the idea behind it is that you apply identities and then decompose this into simple ways, which means I have not told you how many simple ways make up of it, right? But I'm telling you that there are simple ways that make up of it. So essentially, you're coming down and decomposing this into simple. It sounds difficult, but it's actually not that difficult. I'll give you a full-blown example in a second. Okay. Once you can actually decompose it to its simple ways, then you can obviously determine the amplitude, frequency, right, and phase of each of these simple ways. And then you can plot each of these simple ways like you did in your quiz earlier today. And then you can plot the composite, right, because you're summing up at every time point. Okay. So why do I say that it's difficult, but yet it sounds difficult, but it's not really difficult? Because all I'm asking for you is that you can reference any, can you guys see this? Okay, good.
Yes.
Yeah, let me just blow it up a little bit. Fit the width. Okay. So I've given you a full-blown example of what I mean by that. And it's not I'm not asking you to prove trig identities. I'm not asking you to derive trig identities. I'm simply asking you, can you match patterns? The whole exercise is about matching patterns. So it's framed as a trig identity question, but it's matching patterns for purpose of this course, right? So let's assume that I give you the exact same problem, right? But obviously with a different composite signal, right? And I say this, okay, you have a composite signal that looks like this. I want you to break it up into a linear combination, right, of simple ways, which means I should get, at the end of the day, sine, sine, and sine. So these are 3 simple sine waves here. Does everybody see that?
Yes.
Okay. Your goal is to say this. Okay, if I start out with this composite signal, right, I'm going to expand it out in a way that, this is sine 4t times 4 cos, sine 4t times 2 sine. So then you get to this equation. Then basically, right, there are many identities that say, sine A cos B breaks down to this, right? Sine of minus A equals to minus sine A, and so on and so forth. The idea is this. Well, you recognize that there's a sine times cos here, which means I can write this term, right, by this patterning, right, into this. Does everybody see that? Okay. And then you keep doing this. And you can use any identity as long as you show the identity, because this helps the marker to get. So there's no one way to get to the solution, right? What is this exercise all about, right? So this is a non-examinable type of a question, not in your quiz, not in your midterm, not in your final exam. But because it's a take-home assignment, which means that you're given days and weeks to work on it, right? I want you to be exposed at least once on how signal decomposition can actually be done in a formal way, which means, right, the use of trig identities. And the trig identities, and I know that, right, obviously you guys are rusty in it, right? You guys don't really get much exposure to it, but you're not using trig identities as you are proving trig identities as you would if you were taking a math course, right? I'm not asking you to derive new trig identities. Simply, I'm saying this, right, is that I want you to match patterns. So if you notice that there's a sine times cos, there's a known pattern of sine A cos B. Decompose that. There is a well-known thing of sine times sine, because eventually, right, you're going to get a sine squared term here, right? Exactly. The solving part is not painful at all. It's matching patterns. In fact, it's actually an algebraic exercise because you are matching patterns, right, of given identities. Is that clear, Chantel? Okay. So at the end of the day, right, yes, it's a trig problem, but it's not really a trig problem. It's actually an algebraic manipulation problem, right? And what I want you to do is manipulate this guy here, which is the composite signal that I've sort of lumped everything together. And I want you to match patterns and decompose it into into simple waves. And then once you get the simple waves, then everything becomes easy because you can draw a simple wave. Is that clear on what I'm asking you to do? And to go back to your question, Rana, which you asked in the class, can you show me how to decompose that? This is what I'm asking you to do.
Yes, understood.
Okay, so what we did in class was very much just a visual approach, which has obviously, right, limitations.
Yes.
Right, but this is a formal approach, and I want you to experience it. Some students take literally. I've seen students do problems of sort in 5 to 10 minutes. I've also literally seen students work on this for days. Okay, at the end of the day, right, it's the experience I want you to go through. If you guys cannot get a head start by next week, then I'll give you some hints. But I think you can. And I don't want you to take that excuse to not to work to it, because the learning of this process, right, it's actually hands-on trying to work on it on yourself. Okay, so that's sort of the oops, let me close this. That's question 3. Okay, and then question 4 is something that I hope that I can get to today. It's basically I want you to determine what latency is all about. Okay, and essentially all this is that, you know, some student is trying to apply transmit some data, right? And this is actually a real world problem, right? Amazon has for years been trying to see if it can deliver its packages, right, by drones. In fact, right, your goal is this: can I deliver, in fact, streaming video via a drone, right, as opposed through your home network? Okay, and it all comes down to delays, right? And my goal is to say this, right? If I want to deliver this video of this certain resolution and yada yada, right? Can you deliver it? And what speed does the drone have to fly at in order to deliver it? Is that clear? Okay, and so this is your first.
Yes.
Yes, exactly. Okay, so yes, the questions are somewhat challenging, but they're challenging because they're take-home exercises. This is not a quiz. This is not an exam, right? This is where I want you to sit down, read the problem, right, and they're real-world problems. Okay, and can you apply from theory? And usually, right, obviously that's painful, but if you can get through it, you have learned a lot, right? You've gained, in many ways, a lot of insight, right, into the problems at hand. Okay, and your challenge, right, is number 1, right? So the first 2, I think, they're just exercises, right? They should be able to sit down and do and get them through it. This is a real world problem, right? The signal decomposition, right? I want you to experience that, as I said. Okay, if you can't get through to it, I'll provide some help next week. Okay, the next one is also a real world problem, right? Is can we deliver all of the data that we want by drones? Okay, and Chantel might be sitting there. Yep, I would like to have my LAN in 8K, rather, instead of being streamed to me, right? But I want it to be delivered by a drone, right, on a single SATA 3 4 terabyte hard drive. Can we physically do that? Which means, can the drone fly fast enough, right, in comparison, right, to gigabit Ethernet? Okay, so that's your assignment. That's due 2 Mondays from now, and then I'll provide sort of additional sort of guidelines and help as necessary, right, next week. But I want you to all make an attempt to do it. Is that clear? Is that clear?
Clear. Yeah.
Okay, so take it as a challenge, right? Assignments should be challenging. Okay, it's not something that you can just sit down and just, you know, work through it, right, in a matter of minutes, right? It's something that requires some thought. Okay, and the thought process is actually very important. So one of the feedback, right, that we get from sort of doing surveys with industry and so on and so forth, right, is in essence, right, the industry's perspective of BCIT graduates, right, is that they don't have the most or the best, what we call critical thinking skills. You guys, don't get me wrong, are absolutely great, right, at coding. You guys are, in fact, what I would call extremely good code technicians. You can piece together code to produce an output based on a requirement, right? You have no problems with that because you're able to go out and look at Stack Overflow. You're able to piece together. You're able to learn a new framework. You're able to learn a new language. But the biggest comment that we get back from the industry partners that we have, right, is that BCIT students are perhaps not the best critical thinkers, which means BCIT students actually have difficulties deciphering and breaking down the problem that is being asked. And that's the biggest hurdle. And in part, the critical thinking component is what I'm trying to sort of enforce as a learning outcome through this course. Okay? So that's why the problems are written as a real-world problem. You're going to spend time actually even trying to read the problem and understand what it is that you have to do. And that's actually a very crucial problem. And a very crucial learning outcome that you should get. Okay? Okay, that's right, Chantal. Okay, it's a little painful, but I assure you that the pain will be painless, right? Once you can see the end of the light. Okay, so any questions on the assignment? As I said, right, it's not due at the next class, but it will be due the Monday after. So there's opportunities for you to ask me questions again next class. Okay, can we continue on?
Yes.
Oops, sorry, I just clicked the mouse. Okay, so the question then I have now is this, right? We've basically covered an intro to the analog signals, right? And what I want to do now is similarly for the digital signals as an introduction to it. Okay, and we already said, right, a digital signal, really, right, you've been actually very exposed to it. It's essentially, right, you grew up in the sort of the digital world, right? In 2721, right, or 2785, right, more so, I think you were exposed to digital signals than you were to analog signals, right? It is nothing but a signal that has discrete levels, right? So in this case, right, it is a system that's trying to transmit a single bit at a time, right, using two different levels. Okay, a logical 1 using volt level 2, and a logical 0 using level 1. So in this case, right, if I get a signal of this sort, then I'm going to say it's a 1 0 1 1 0 0 0 and then a 1. Right? Everybody's seen this. And then I motivate it, right? Even with the analog, you can increase the data rate. Obviously, right? If you have a system that's 8 bits per second, Chantal, are you happy with that? A system that simply functions at 8 bits per second. I would think that it's unacceptable, right, Chantal? I mean, exactly. I mean, I don't think that's really slow. That's in fact in today's world unusable, right, Zisang? Can you imagine if you are receiving 8 bits per second on this bongo session? You know what? We can't do the things that we actually want to do. So obviously, we want to increase data rate, and one way to increase data rate, right, is obviously to transmit more than 1 bit per transmission. But the question now is this, right? Is that now if I want to transmit more than 1 bit, I need more levels, right? So 1 bit, 2 levels, 2 bits, 4 levels, right? 3 bits, right? 8 levels, and so on and so forth. Remember, right? Oh, I think it would take more than the whole day, Zitang. I think that we might have to use the whole year to do so. I don't have a estimate of what this bit rates are and so on and so forth in terms of encoding, but we can actually calculate that, right? What the total data rate requirement is for this transmission of this bongo with the audio and the streaming of the slides at the same time, right? And obviously the quality matters, right? So I think it will take more than that. But in any case, right? We motivated this in analog, right? Is that if we want to transmit higher data rates, which means we want to transmit more bits per transmission, then we would need to have more levels. And obviously, right, the problem lies with Albert, right, as to why we cannot have infinite data rates, because he's unable to come out, right, with a system that produces infinite power, which means I still cannot have unlimited data rates because I'm capped by the power just as I would in analog, which means I need to maintain, obviously, a certain delta between the levels, right? And I need to maintain, right, a maximum amplitude that I can use in the transmission of these signals. Okay? So just so you know how I got in terms of 1 bit, 2 levels, 2 bits, 4 levels, 3 bits, 8 levels, right? It's actually using the log function. right? If I tell you this, right, is that a system has 8 levels. How many bits are required? Well, in your mind, you know it's 3 because you can count 0, 0, 0 all the way to 1, 1, 1, right? So that gives you between 0 and 7, right? But effectively, right, the log function gives us the exact same value as well, because I can just say this. Okay, if I want to have 8 levels, and I'm computing 8 levels in base 10, obviously, right? Because I'm counting from 1 to 8 in base 10. In binary form, that would require me to use at least 3 bits, because then I can count from 0, 0, 0 through to 1, 1, 1. And that's what the log function is really for. And that's how we're going to use the log functions, right? Is that we care about, right, the representation of values in decimal. So in this case, in 8. And I'm trying to figure out, well, if I'm going to use a base 2 representation, which is in binary, how many bits are required? And you've been exposed to this in 2721. But this is the formal use of that. Okay. So because the digital signals are usually non-periodic. Okay. So we don't have the concept of periodicity in digital signals. What we have is instead, right, we compute the bit rates. So this you guys are very familiar with, right? Because you want the highest possible bit rate, right? And we always express, right, in bits per second. Does everybody follow? We always express this in bits per second, right? Our reference of time throughout the entire course is always going to use the time resolution on per second basis. Okay. Similarly, if we wanted to compute the bit rate or the data rate, it's the same thing. Bit rate just means strictly bits per second. Data rate could be expressed as bytes per second, right? Words per second, characters per second. It doesn't really matter. At the end of the day, right? My goal is to express everything, right, in bits per second. Okay. So if I tell you this, right, oh, I'm going to now download some text documents, right? There are 24 lines, there are 80 characters per line, and I'm transmitting at 100 pages per second. What is the required bit rate of this channel? Anyone? So this you should be able to do within a matter of a few seconds. How, instead of giving me the number, how do you approach this problem? I have simple text documents. There are 24 lines, right, per page, okay? And there are 80 characters per each of these lines. And I want to transmit 100 pages, right, per second. How much data rate do I need to transmit that? Exactly, okay? So the missing component here, right? And the reason why I give this example is that you need to know how many bits a character represent. And usually, right, we use 8 bits.
I'm assuming yes, yeah. I assume
exactly in ASCII. Okay, but each character does not have to be 8 bits. We have gone from 8-bit ASCII coding, right? We've now moved to 32-bit Unicodes. Does anybody know why? So it used to be every character was represented strictly based on 8-bit ASCII. But the times have changed, and the problem is actually you guys. Okay, it used to be that there is enough combinations in 8 bits, which is 256, to define keystrokes and combinations of keystrokes, right? Like if you type Shift K or Alt K or whatever it is, right? There are enough combinations for us to define an ASCII code in 8 bits to represent that. But we have moved away from 8-bit codes. In fact, we are now at 32-bit Unicodes, right? Are you guys aware of that? And potentially at some point in our lives, maybe we have to go down to 64-bit Unicodes. Okay. Part of the reason is because of you, and I like to use you as in your generation, right? Because you guys now effectively do not just simply transmit characters. You guys now want to transmit something known as emojis.
Don't emojis have corresponding alt certain number?
Yes, exactly.
Alt?
But yeah, exactly, they do. So that's why 8 bits are no longer sufficient. We need to use 32 bits, right, in representation. Right? In fact, most of you, right, as I've seen some of you communicate, right, you communicate actually not using text anymore. Have you seen individuals communicating text messages strictly using emojis only? And your request for emojis, right? Yes, exactly, right? Is never ending because you need an emoji for a salami pizza, like which is like pepperoni. Okay, you need one that's a Hawaiian pizza. I don't understand that because I don't use emojis at all. In fact, I disable the emoji keyboard on my phone. Right, there you go. Okay, there we go. Welcome, right? You guys are part of the reason why we have to keep studying data communications, because you guys keep increasing the need for the data rates that we need. Okay, so in any case, so this is how we compute that. And why did I show you this as an example? Because I want you to be able to compute, obviously, right? Video streams as well. So that was characters. What about high definition television? Supposedly, right, I want a full HD quality, which is 1920 by 1080 pixels per screen, right? So that's 1920 across, 1080 vertically. And I want to do a 30 frames per second, right? So this is what this is. In these cases, in fact, you guys want 4K at 60 frames per second. Okay, let me ask you, if I simply have full HD, which is 1920 by 1080, and I'm renewing at 30 frames per second, right? And each pixel requires 24 bits. How much data do you think is generated per second?
1920 times 1080 times 30 times 24.
Exactly. Okay. 1.5 gigabits per second. Is that a lot of data, or is that very little data? To put it into context, have you seen a single bit? Have you seen a single bit? Like a 1 and a 0? That's 2 bits already. Can you imagine? We need 1.5 billion bits per second to transmit full HD. 1.5 billion bits per second. Okay, and then if you can do that and extrapolate that to 4K, you can extrapolate that to 60 frames per second. So I don't know why you guys are complaining that your cell phones, in fact, do not have all-day battery life. Right? Essentially, your processors have to, right, process this amount of data. What is NeoCan? I don't understand that. Shankai, what is NeoCan? The text messages that you guys write these days are so cryptic. Oh, I see. Okay, so I see. You know what? I don't. I cannot understand that. But in any case, right? Can I ask you another question? What is the data rates that you guys get from your service providers at home? It's okay. You don't have to be sorry. Right? In fact, I want some participation. It's just that it's a generation away from me. So some of the things that you write, I don't fully understand. But what is the nominal data rates that you guys get from your service provider? Does anybody know? Anyone? When you subscribe to your sort of a service provider service, right? What kind of data rates do you get? There you go. So if I tell you, right, one channel requires 1.5 gigabits, how is that possible? Anyone? How do you actually get 1.5 gigabits per channel? And how many channels do you have on your television sets these days? Assuming you still subscribe to cable television. How many channels do you have?
It depends on the package.
Exactly. Okay. So this is unattainable, right? And part of the reason it's unattainable is because it's an overwhelming number of bits. It's 1.5 billion bits per second per channel. So what do telcos do? Service providers compress. Okay, and it's through compression of removing of the redundant information, removing of the high and low tones, removing information that is not necessarily primary, right, to all of these display of audio and video and content. Okay, so what stations do is that they actually never transmit at 1080p. They always transmit only at 720p, and then your television box and your television in conjunction will extrapolate that to a 1080p image. Okay. Exactly. So that's what we call rate. So that is actually called the rate distortion algorithm. That rate distortion algorithm was actually created by my advisor at Cornell when I was doing my master's. His name is Toby Berger. Right. So what Shankai is saying is that we don't transmit the primary frame all the time. We don't transmit all of these pixels. We only send the deltas. So only frames that have changed, only pixels that change from frame to frame. And then every X amount of time, we refresh the entire image. Okay, so this is how we deal with images, right? We compress, we don't transmit as much information as we need because we want to save on the amount of data transmission that's actually absolutely necessary. Okay, so you need to be able to compute this, right? In the case of the drone, and in the case of the drone, I'm saying that you're trying to transmit uncompressed video, right? Which means in its raw form. Okay, so because we don't have the concept, right, of data rates, right, I mean, in terms of periodicity, right, in digital, right, we also don't have sort of the idea of direct comparison to wavelength. But what we do have is the bit length, right? And the bit length is actually defined the same way as what the wavelength is, right? It's just that how much, right, distance, right, each of these bits occupy. And it's again, right, if you recall from physics, right, distance, right, which means how much you travel, right, is nothing but speed times time. Okay, so the analogy or the corresponding metric, right, for wavelength in analog, right, is bit length in digital. Okay, now let's get to the interesting part of digital signals. Okay, and I want to spend a few minutes here on sort of the interesting concepts behind digital. Remember we talked about bandwidth? What is bandwidth? And does anybody remember what is our definition of bandwidth? F high minus F low, exactly. Okay, Yonju 1. Okay, what do you think is the bandwidth required for a digital signal? How much bandwidth do you think digital signal requires? Anyone? Actually, the bandwidth requirement for digital signals is infinite. Think about that for a minute. Does that make sense? What does it mean to require infinite bandwidth? It means you require all the frequencies in the world. True? Right? That's what infinity is, right? You need something from 0 all the way to infinity. Is that a practical requirement? No, exactly. Why? Because there's only one infinity. Right? Which means that if I want to transmit a digital signal, I'm going to require transmitting from 0 to infinity for that particular transmission. So how many transmissions can I have? I can only have one. And you can reach infinity. Okay? So then the question is two, right? Two questions. Why? Number one, why is it that the bandwidth requirement is infinite? And number two, if it's truly indeed infinite, then why are we still using digital signals? In fact, most of our transmission, right, in terms of the devices that connect with each other, right, it's actually digital transmission. We're transmitting using digital signals. So why is it that we're still using digital, right, when it's infinity? So let's answer the first question first. Okay. This you don't really need to derive, right? But I'm going to tell you that obviously the key takeaway from this is that the requirement for digital signals, right, in terms of bandwidth is infinite. Okay, I'll show you a diagram first, actually. So I want to move this away from this, and I'll show you a diagram. Okay. Okay. How do you think digital signals are being created?
Pulses or voltages?
Actually, not really, because what we have is that in sort of signal generation, there's usually created based on the clock. And a clock is actually an analog device. It's an oscillator. Does everybody know that there's actually an oscillator within your computers? Exactly. There's something oscillating. Okay, so if you look at sort of the clocks, right, within a simple computer, right, you must have been exposed to this in 2721. There's the notion of a clock, and a clock is an analog device because it's nothing but an oscillator. It goes bang, 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 and so on and so forth. Okay, effectively, right, how we create the signals, and you were actually slightly exposed to it in the example of the composite signals that we showed a minute ago, in that what we did was if we have a wave that does this, then I do another one that is at double sort of the frequency. Then I do want to sort of triple the frequency. Does everybody follow? The more I do of this, the flatter the top I get as a composite signal. Does everybody see that? Right? I mean, remember this particular slide that, oops, oh, I shouldn't have done that. I wanted to switch back to the deck of slides here. Here. Remember this guy? If I go back to sort of the waveforms that make up of it, this is the first harmonic. Then I add on the third harmonic. Then I add on the ninth harmonic. Does everybody see that in the composite signal, this top here is getting flatter and flatter? Are you guys able to see that? Essentially, that's how digital signals are actually created, right? Is that I'm going to give you an infinite number of harmonics, right? And if I give you an infinite number of harmonics, this eventually becomes a flat top. And this obviously becomes a flat bottom. And this would create for us, right, a digital signal that looks like this. So if I get back to the right mode, pause the screen here. This will get us these flat tops here. Okay. So there are two ways to see why. And again, you don't need to know how to derive the fact that digital signals require infinite bandwidth, right? So that would be a graduate level type of exercise that you would do. But I've just demonstrated to you, right, in this particular diagram here, is that if I now use infinite harmonics in generation based on the oscillator, this is eventually how I create a flat top. So what does that mean? Then I would need, obviously, frequency ranges, right, from f equals to 0 through to f equals to infinity. Right? Sorry, because I was writing that in a very small screen. But essentially what I'm saying is that I would need then, obviously, frequency equals to 0 through to frequency equals to infinity. So that's the intuitive side as to why a composite signal requires infinite bandwidth. Okay. If you ever read sort of Appendix E, there's a section in there that's called Fourier transform that you're not responsible for. Fourier transform simply says this, right? Any spikes in the time domain, which you see here, these are the spikes, okay? That actually results in a frequency of infinity. Anything that's a line, which we saw, which is DC, actually has frequency of 0. So in fact, this is the same, right, from a mathematical perspective, why a digital signal goes from 0 to infinity. Okay, but at the end of the day, right, you just need to know that digital signals require infinite bandwidth. Okay, and the question then is this, is that if a digital signal requires infinite bandwidth, then why is it that we still use digital signals? And we argue that that's a bad thing. Okay, so the question is, why are we still using digital signals? Anyone? Analog. Right, we started off the world as analog transmission only. And then eventually, right, we did digital. Okay, I'll tell you why. Okay, the reason is because digital signals, we have many what we call digital signal processing techniques, DSP. Okay, essentially this is what DigiPro does. Okay, we can do things like compression. Okay, in fact, what we want with digital, right, and I'll show you in a few moments, is that we want to transmit actually the minimum of information as long as the signal can be recovered. Okay, so we can do a lot of things like digital signal processing techniques, right? And you've seen some of those, right? Who's sort of used digital filters? So if you're taking a selfie of yourself, right, you can apply sort of a Gaussian filter, like a blur filter, right? You can sort of, and I don't know of all the filters. I don't use any of those tools, but I know that you guys would will artificially, right, change the images that you capture. True? Through digital signal processing, right? Anytime that you take a picture, right, Photoshop, exactly, right, and you're applying filters to it, you're effectively changing the data content, right? Whether it's a smoothing filter, which means that you're evening out the tones of your complexion, right? If you ever look at sort of the Instagram profile picture of Ziteng Liu, right? He has perfect complexion. I don't even know. Maybe he does have perfect complexion, but it is not only perfect complexion, but it's extremely even toned, right? In fact, some of you go beyond of just perfecting yourself. You go and create a make-believe of yourself, which means you go further than what you really are, right? Okay, so that's what digital is being used for, right? We've gone through all these years, right, of trying to sort of use digital signals. But I want to show you another thing, right, of why we also continue to use digital. Okay, let's take a look at it. Okay, so the motivation is still the same, okay, in terms of properties and theorems. A digital signal, right, obviously, right, in the periodic sense, will have spikes in the frequency domain. A digital signal that is non-periodic, obviously, right, is actually going to be a continuous curve. Right, so this is the same. The only difference, right, in digital is that obviously in both the periodic sense and the non-periodic sense, they both go to infinity, right? So this just means that there is more to come. Okay. The problem is this, and I said that this is a bad thing, right? Because in real life, we do not have channels, right, that are infinite in bandwidth. We don't have that. We have one. But most channels that we use do not actually have infinite bandwidth. Right? So some of them we use have very wide bandwidth, and some of them that we use have very low bandwidth. And we saw an example of this when we were dealing with the MP3s. Remember, if I can see the frequency response of a signal, I can determine what I can actually essentially remove. Right? Because I don't have to transmit the signals that have the frequency components that have very low frequencies, low amplitudes. Right? In the case of audio files, right, I can remove the high and the low tones. So if I show you this example, this is the signal bandwidth, right, in terms of the spectrum for a digital signal, right? So number one, you know it's digital because it goes from 0 to infinity. Number two, right, you know it's non-periodic because it's a continuous curve. But the important thing is this, is that you will notice that the very low frequency components and the very high frequency components, they have very low amplitudes. Does everybody see that? Okay. Which means, right, if I now put this through a filter, which obviously this is your medium, right? So your channels themselves do not have infinite frequencies. If I put this signal through this, effectively what I'm saying is this, okay, I'm allowing only the frequencies between F1 and F2 to pass through, which means I'm going somewhere from F1 to F2, and these are the frequencies that will go through. Which means I'm eliminating any of the low frequencies and I'm eliminating any of the higher frequencies. Okay, from a sort of visual point of view, in the time domain. So this was the frequency domain. This is the time domain. This is a digital signal, which requires infinite bandwidth. I'm putting it into a wide bandwidth channel, but nonetheless, there's still some clipping of the high tones and the low tones. And this is the output signal that I get. So let me ask you a question. When you look at this output signal here, does it resemble this input signal?
Not quite.
Not quite. But do you think I can actually, I mean, it's not exact, but do you think I'm able to reproduce this input signal from this? Exactly. Right? Does everybody see that? Because in digital, I only need to know a couple of things. Really, I want to know what level this is at, and I want to know what level this is at. And the only other thing that I need to know are the transition points. Which means I've effectively said this. A signal that initially required infinite bandwidth to transmit can be transmitted using much less bandwidth as long as there's a way for me to recover this signal into this. So effectively, right, I can start reducing the frequencies required as long as I can recover this output signal that is received back to this input signal. So we effectively, right, have flipped the problem. Instead of saying that, you know what, requiring infinite bandwidth for a accurate reproduction is necessary, we've twisted the problem in a way that we say this. In fact, what is the minimum amount of frequencies required, right, which is the bandwidth, to transmit a digital signal? As long as I can recover it, I can transmit using the minimum amount of bandwidth required, right, which obviously now changes the problem, because the goal now is recovery and not exact reproduction. Does everybody get that? So why is digital sort of being pushed as the transmission sort of technique in the last few years? It's because of a couple of things, right? Number one, signal processing, right? Sort of what Z-Tang is saying, right? You can obviously, right, manipulate the digital bits, right, using modern day digital signal processing techniques. Number two, in fact, right, what we have with digital is this, is that we've come to a point where we're saying this: what is the minimum amount of transmissions in terms of bandwidth required? As long as I can recover that, then it doesn't matter that it actually requires infinite bandwidth, because I'm never going to attain that. But what I want to do now is the opposite of what I intended to do, and is to transmit it with the least, using the least amount of bandwidth. Does everybody follow the argument? Does everybody follow the argument? In fact, I've twisted the problem, right, in a different way.
So we can say it becomes recovering the signal rather than reproducing the signal.
Reproducing the exact signal.
Yeah. Right?
We're recovering the exact signal rather than trying to transmit the exact signal. And that means I've gone from a problem that actually initially requires infinite bandwidth to a problem now that says, what is the minimum bandwidth required to transmit the digital signal? Is that clear? Okay. So then, obviously, there's two terms I want to introduce you, right, to sort of wrap up on digital signals, right? The idea of baseband transmission versus broadband transmission. Okay, baseband just says that, right, you're starting from zero all the time. So our human voice, right, is in baseband. Okay, broadband transmission just means that you do not start from zero. Okay, so some of you may have seen diagrams like this, right, that you might have been exposed to notions of something known as a low pass filter. This is a low pass because it starts from zero, right? This is a low pass filter. You might have seen things like a band pass filter, because it allows you from F low to F high. And you might have seen things like a high pass filter, which means you start at a F low, but you go to infinity. And this is a high pass filter. This is your baseband transmission, right? Which is human voice, right? We transmit our human voice in baseband. In broadband transmission, right? This is your broadband transmission. The example of this is, who's listened to a radio station before? Anybody listened to radio stations before? Yeah, okay. Can you tell me, in all of the transmissions of the radio stations, is the content the same type of content? Not identical content, but is it all similar content? What I mean by, is it just human voice with music, like instruments playing? Right? Whether it's 94.5, 95.3, 96.1, doesn't really matter, right? I mean, it's similar content, right? They're not identical, but they're similar. Why is it that we need to transmit radio stations, right? So if this is the FM band, and it goes from 88 megahertz to 108, right? Usually what we denote it by is we show this. These are the different radio stations. This is 94.5. This is 95.3. This is 96.1. The content in here, they're all similar, human voice and musical instruments playing. Why is it that I'm transmitting in broadband? Why don't I transmit everything in baseband? Because we know human voice is baseband, right? 0 to 4K. radio station 1, radio station 2, radio station 3. Why don't I just do everything in baseband, sorry. Audio only, not just that, but I could say this, well, let's go to 22K, right? Because that's what the instruments will get onto. I can say, why don't we do it to 22K? Why is it that I need to use 94.5 megahertz, 95.3 megahertz, and 96.1 megahertz? What will happen if I have 3 radio stations all transmitting in baseband? Exactly, because you can have a different channel. If we all do single, right, baseband, effectively, right? If I talk and you talk, what happens? Interference, right? So broadband transmission allows us to channelize, and we call this technique frequency division multiplexing, and we'll see that in a few weeks, okay? But essentially, right, what I'm trying to show you here, right, is that the reason why we do the different types of transmission, right, in particular, right, if we are trying to do sort of a broadband transmission, is because we can actually channelize. That's right. So if you talk at the same time, then you're interfering, and my ears will pick up multiple transmissions. But one way to take a look at it, right? Anybody seen a piano keyboard? Has anybody seen a keyboard before? Yeah. So the notes are C, D, E, F, G, A, B, C. True? Okay. But each time you go from the left to the right of the keyboard, you're increasing in an octave. True? Right? Are they all the same notes? C, D, E, F, G, A, B, C. But they're slightly an octave higher each time. I mean, what I mean is they're all C, D, E, F, G, A, B, C. Do, re, mi, fa, sol, re, so, right? But they're an octave higher. Essentially, right, the example of bandpass channels is essentially that. Let's assume now, right, if I get pitch is different, of course, okay? But the thing is this, if I can now, again, have Rana demonstrate that she's talking, right? And if I can have Chantel also say something at the same time. Can you both say something at the same time?
Hello, good day.
Definitely.
Okay. Okay. So let's pause that for a minute. Okay. So does everybody see that there's interference because they're all transmitting at baseband? But if I say Chantel, I want you to raise by an octave. So instead of using your baseband from 0 to 4K, I want you to now raise everything by 4K. Say the same thing, but raise the pitch up from 4 to 8K. Do you want to attempt to do that?
I don't understand what you're asking.
No, I'm just saying that, can you raise your pitch?
I don't know what you're asking.
Right, exactly. So if Rana continues to speak at baseband, I now can tune to a different channel and in fact receive 2 streams of information simultaneously. Does everybody get that? That's why we have radio stations. It's effectively, right, using the wide range of frequencies available at a higher frequency so that we don't always, right, interfere with each other at baseband. Okay, so this is just an intro to all the concepts, right? No, so the notes that you're playing are the same notes, C, D, E, F, G, A, B, C. But the frequency, right, and what you would call pitch, right, is different because you're going 1 octave higher each time. And if I say this now, that my ears are able to listen, right, in 2 different channels simultaneously, and you're transmitting that, then I now, right, so the piano keyboard is an analogy of what I'm trying to do here, right, is I want to transmit everything in broadband, right, like how I channelize the radio station 1, radio station 2, the radio station. In fact, the contents are all the same, but I've effectively brought them up to a higher frequency so that I can tune in and listen to multiple transmissions simultaneously if I so want to. Okay? Any questions on that? Any questions? Oh, no, it's the example is simply this, is that the notes that I'm playing are the same. I'm playing C, D, E, F, G, A, B, C. But I can have multiple different pitches or frequencies of the notes across the keyboard. So in baseband, right, I'm trying to transmit human voice. For example, Rana and Chantel speaking at the same time. But if they were to speak at the same time, right? They will interfere with each other a bit because they're both using the same base frequency. But if I say Chantal needs to raise her frequency by 4K, which means her vocal range is now between 4 and 8K. Effectively, if I have two 4K filters, I can listen to two streams of the message at the same time, just like in a radio station. That's right. Okay. Any other questions? Okay, so let's take a very quick stretch break here. I really would say just 5 minutes, and then I want to get on to the next module, right, if we can, for the remaining 30 minutes. Okay, let's take a 5-minute stretch break for everybody here. Yoon-bin, how are you displaying your two sessions? Like, are you having one on the laptop? Like, how are you using the two sessions? I'm just curious. No. But what's the benefit though, like having the stream displayed twice? No, I'm just curious. What's the benefit? Like, how are you optimizing the use of this, having two screens? Like, oh, do you want to sort of share with us what the benefit is? Because we're trying to see how we can make sort of the e-learning experience better for everyone, right? So I'm just trying to figure out, like, if we can allow users to have multiple streams of this, right? What's the benefit? Oh, I see. Okay. No, because you're in listen-only mode. So to talk, right, you need to be in microphone mode. I see. No, that's fine. No, because what I would like to put a request to Bongo is that actually I can share two screens. So I don't have to keep switching between this and this and this and this. I like a whiteboard to sort of be persistent, right, on the screen all the time. In fact, I also would like to be able to share two applications. Like, I want to be able to share a PDF and a PowerPoint at the same time, if possible. So if there's a way for them to do a top and bottom screen on this Bongo session, that would be awesome. So that would be sort of really nice for what I want to use it for. It is, but then the problem though is that if I do that, right, I don't get to see your chat messages anymore.
So what if you actually use 2 monitors? And you can choose which monitor to share.
No, it doesn't share by monitors. Monitor is just how it's displayed. It shares by applications. Right? I cannot do monitor sharing of monitor 1 and monitor 2. That's not how it's delineated. It's delineated based on desktop versus applications. Exactly, but that's okay. I mean, it's just something that I was hoping to be able to sort of do, is to do 2 screens at a time kind of thing, right? So I have a lot more flexibility. Yeah, 2 applications, but then obviously my screen, I guess I could, yeah, because I can only write on my laptop. I cannot write on my monitors. But I want to try to, because I know that very likely that we have to move online next term as well, and I have all the different option courses to run, and I'd like to be able to write and show the slides at the same time, just like if I have a whiteboard and my deck slides. That would be ideal for me, but we're still limited in anyways. But is the audio coming through well? Are you guys following me well at all?
Yes.
I see. Okay. Right. Yeah. So I have to take a look at different things and see how we can make this even better. Okay. Is everybody back from your stretch break?
I'm here.
Yeah. Okay. So I want to sort of move away. We're still in the introduction, right? But I want to address some other additional issues, okay, as an introduction. And then obviously all of these will continue to get dealt into more details as so the course progresses, right? But there are a couple of things that we want to talk about. So we talk about the generation of signals, right? But we effectively have not talked about, right, what if there are noise in the channels? We're assuming that everything is transmitted ideally. So this is what we transmit. This is what is being received. True? But that's not the real world. Okay? So I want to spend some time to talk about transmission impairments, right? Which means how can the signal that we transmit essentially be impaired? Which means what is received is not really what was transmitted. Okay? And then the next thing that we'll extend from there is this. Okay, well, if we now know that this channel is impaired, then the question is, how does it impact the number of bits or the amount of data we can actually transmit? Which means that if I now say this, right, I'm giving a lecture, okay, and I know there's an impairment. And impairment is coming from Rana because she's always doing a background hum. Like, can you do that, Rana? Can you just hum something continuously? Like, just make a tone, right? And then I'm trying to talk and give a lecture and so on and so forth, right? Does everybody feel that obviously if she hums even louder than that, right, you guys will find my speech impaired? Does everybody feel that? Exactly. Okay. So that's what I mean by transmission impairment. And then the next question obviously is that if I know that there are always impairments in the system, okay, then how can I ensure that you still receive the data correctly? So one thing I could do, right, is, Rana, can you do the hum again? I can try to speak even louder, or I can try to say everything twice. I can try to say everything twice. I can try to say everything 3 times. I can try to say everything 4 times. Does everybody see that? Because I'm trying to fight the impairments that she's introduced into the channel. Okay, which means effectively, right, my data rate will go down. Okay, so we're going to look at that, right? Is okay under this condition, right? If there's impairments or signals, right? How do I actually sort of continuously be able to give you data, right, that is unimpaired? Which means the transmission is impaired, but what you receive should not be impaired. Which means I could say everything twice. Right? In fact, one of the best ways of ensuring that there is reliability, right, is called repetition code. If I just keep saying the same thing. Okay. And then the last but not least, right, in 3.6, I want to talk about performance, right? But really the computation of latency. Okay, I'm suggesting actually now that I actually will not cover 3.5 and 3.4 and 5 today, but I want to skip right to 3.6 today first, because that pertains to your assignment 1, question 4. Is that okay? We'll come back to 3.4 and 5 next week. Okay.
Do we need to know anything from 3?
No.
Okay.
No, they're completely separate introduction topics, because we're still in the introduction sort of phase.
That sounds good. Yeah.
Yeah, exactly. So the reason I want to do that so that you get more thoughts into the assignment that you can work on, right? Instead of only teaching you next week and then it's due Monday. Okay. So the idea is that in the next 20 minutes, right, when I cover through this, right, you will have the ability to do the entire assignment. Okay. So right. Well, assignments are always fun. Right, you should approach them as a challenge, and you approach it, having fun rather than being a chore. Okay, so the idea is that you're learning something, hopefully, right, doing the assignments. Okay, so the idea is this, right? We transmit data, right, and we said that we're doing it over signals. Okay, we have analog signals, we have digital signals, right? But that's only really trying to increase in many ways, right? What's known as the bits per second. True, right? We only care about how much data we can actually transmit. But what we don't actually measure, right, is does the channel allow for that, right? And the different types of computation in terms of how many bits per second we can transmit. And as well, a very important criteria is the delays experienced by the bits, right? Because remember, right, when I told you guys at the first class, right, you guys came back with 2 requests. Minimally of 2 requests, right? You want very high data rates and you want very low latency. Okay, and we'll take a look at that, right, in terms of performance measures, right, in this introduction section. Okay, so remember, we can measure sort of the performance, right, and the notion that we use, right, obviously is bits per second. Okay, so unfortunately, right, throughput and bandwidth have sometimes been used interchangeably. Okay, remember, right? Our notion of bandwidth is strictly f high minus f low. But there's an alternate use of the word bandwidth, unfortunately. Okay, and I wanted to share that with you first. Okay, there is the bandwidth in hertz, which is obviously what we did, right? F high minus f low. Okay, but there's also the bandwidth in bits per second. But this bandwidth is not actually the throughput that you use, but this bandwidth is really the speed of the bit transmission in a particular link. For example, right, a fiber optic cable itself may have a limitation of 1 gigabits per second. That would be its bandwidth, which means we can transmit up to, but not exceeding 1 gigabits per second. All of these standards that we use, like for example, in the assignment, I say that there's a SATA 3 interface, and the SATA 3 interface has a bandwidth limitation, and you can easily find that. I did not tell you that in the assignment, but that's information you can easily find. Right, Ethernet cables have a certain bandwidth, right? If you're using 1 gigabits per second Ethernet, right, the maximum, obviously, right, speed of bit transmission is 1 gigabits per second. So just so you're clear, right, the definition I stick to most of the time, right, really is in bandwidth in hertz, and that's our sort of fundamental definition of bandwidth. But there are times where bandwidth is used in the context of bits per second, right, and obviously that's the limit, right, of any link or medium. Okay, but what you care about as an individual is that even if you have a 1 gigabits per second link, you are very unlikely to be transmitting at 1 gigabits per second. But more so, you are assuming a particular throughput on the system, which means your average usage on the network, right, could be 200 megabits per second on a gigabits per second network, which means as long as your throughput is less than your bandwidth, then your data, obviously, right, would be transmitted across that link, right? So very much so, right, throughput is usually bounded by the bandwidth. Is that clear? In terms of definition, and this is really just a straight out definition of the terminology. Okay, so that's throughput versus bandwidth. The next thing I want to sort of discuss, right, is actually latency, and this is the part that's actually really fun for your drone. Okay, when you transmit something over a network, what do you think contributes to the delay in you receiving the data? What are some of the examples in which the data can be delayed? Anyone? Routing, sure. Okay, so routing, and obviously routing because it is a routing process, right? But I would take routing because of the distance, right? So what I mean by this is this: when you transmit something, does the file size matter in terms of the delay it will take to transmit that file? Does the file size? Does it take the same time to transmit an 8 terabyte file versus a 1 kilobyte file? Does it? Shenkai, does it take longer to transmit an 8 terabyte file versus a 1 kilobyte file? Or are the times to transmit the different sizes and file sizes the same? Yeah, exactly. I mean, you must have experienced that, right? If you try to drag an 8 terabyte file from your hard drive onto your external drive, it would take hours. But if you try to drag, right, a 1 kilobyte file out from your hard drive, right, to external drive, that would probably be almost instantaneous. Then the next question is this: does the delay in distance matter? What I'm saying is this: when you transmit a file across a network between devices on your home network, do you think that experiences the same amount of delay as if you were to transmit the same size file to BCIT's network? Should there be a difference? Shenkai? Or Edward? Should, obviously, right? I mean, you give the extreme, right? If you're trying to transmit a file between Vancouver and Toronto, right? Obviously, it should take longer, given the same size file, right, when you transmit between Vancouver, right, and Richmond. Okay, so what I'm trying to say is this: in fact, the latency that one experiences for end-to-end transmission of all of these data is not just one single parameter, but rather a collection of components, right? So from an academic point of view, right, we'll look at things like propagation delay, transmission delay, queuing time, and obviously processing delay. And I'll argue for you that, in fact, right, the propagation delay is the time that it takes as a function of distance. So first of all, the bits needs to propagate, right, from Vancouver to Toronto, right? Obviously, that would be different amounts of delay, and I call that propagation delay because it needs to propagate the distance, right? So the distance matters whether you're from Vancouver to Toronto or Vancouver to Richmond, right? So by equation, right, the propagation time is nothing but a function of the distance over the propagation speed. Is that clear? That part of the delay is actually experienced because of distance. Does everybody get that?
It's clear.
Yeah, so if there is the component of propagation delay, then what do you think is transmission delay? So propagation delay is easy to visualize, right? Because it's distance, right? I mean, it will take you longer to drive from Vancouver to Toronto than Vancouver to Richmond, right? Same thing. The bits have to travel a certain amount of distance, even though it travels at the speed of light, but it's still, right, a function irregardless. So then what do you think is transmission delay? I'll give you a hint, right? It's got to do with the file size. Exactly, right? Think about it, right? Before the bits can actually propagate the distance, you have to put the bits onto the medium, right? Which means, right, dragging a file size, right, like not dragging is just like a drag and drop, but putting a file size, right, of 8 terabytes onto the medium should take longer than putting a 1 kilobyte file size. True? Because in one case, right, there's 10 to the 12 number of bits. In the other case, there's only 10 to the 3 number of bits. Right? There are multiple orders of differences. Okay? So transmission time is really the time that it takes to put the data onto the medium. Propagation time is the time that it takes for the medium to travel the distance. Is that clear? So in the context of the drone, this is what you're playing with. Okay, these are the two factors that you're trying to compare against: is what is the propagation time over GBE, which is gigabits per second Ethernet, and what is the propagation time, right, to go over a drone? What is the transmission time to put this file size over this interface, which is gigabits per second, and what is obviously, right, the transmission time to put it through a SATA 3 interface? Okay, essentially, right, the latency, as we will be exposed to, is made up of 4 components. It's simply the addition of all of the delays that we can experience. In the drone problem, you only have to care about the propagation time and the transmission time. You can ignore the queuing time and you can ignore the processing delay. Is that clear? Any questions on the definitions? So let's take a look at another consideration, which is called jitter. And we will not consider jitter in this problem. Jitter is who's experienced jitter? Not in sort of public speaking, but who's experienced jitter in terms of data transfer? Anybody experience something known as jitter? And if you have, right, how would you classify that? So jitter as a concept, right, is very different from latency. So the latency is the wait time, right? So if something is delayed, right, this is the amount of time that I have to actually wait. Jitter is actually, yeah, like in video streaming, right, there's some jitter. So some packets may come a little faster and some packets may come a little slower, okay? Jitter is actually a measure of the difference in delay of each of the packets coming for a stream, which means the delay that each packet experiences on the network may not be exactly the same. So sometimes data comes a little faster and sometimes data comes a little slower. And the problem now is this, if the deltas between the average delay is very small, then obviously you can have a very smooth playback. But if this starts to have a very wide variance in terms of the deltas of delays, then what happens is that it becomes very difficult to buffer for the large differences in the delays of each of these packets. And therefore, sometimes when you play back video, it's not smooth. You get this sort of quick playback sometimes, right? And then sometimes a slow playback. And that's what we would define as jitter. And it's most prominent in voice over IP because our human ears can pick that up very easily. Okay, just so you know, right? Empirically, they have done studies, right, that defines this, right? Do you know your human ear is sensitive to delays to up to 140 milliseconds? So they've done all these tests, right? Is that they've determined that the human ear can pick up delays if the delays are greater than 140 milliseconds, which means, right, if I say something and there's less than 140 milliseconds between each utterance, which means each word that I say, your ear will pick that up as continuous, smooth playback. But if I start to talk and I say and deliver the lecture this way, does everybody see that now? You're starting to pick up pauses. Does everybody feel that? Because the delays now between every utterance that I make is actually greater than 140 milliseconds. Okay, and your ear starts to pick that up, right, and sort of break it within the speech. But in any case, we will not consider jitter because you need to know a little bit of probability and statistics and distribution, right, to understand that. So in the last question of assignment 1, you're focused strictly on propagation time and transmission time. No, lagging is when it's not jitter. Lagging is when there's delay. Okay, jitter strictly talks about, right, the difference of the delays of every packet, right, in relation to the average. So mathematically can actually be defined is how far off is the delay and the distribution of that delay, right, of every packet with respect to its average. Lagging just means that it's slower, but jitter can be faster as well. The jitter is sometimes you're faster than the average and sometimes you're slower than the average. So you're not always lagging. Okay, Zishan? Okay. So let's do some examples, okay? And I want to wrap up with the 2 examples I want to show you, and then we're done for the day, okay? So let's assume I've tell you now, right, that a bandwidth, right, a network has a bandwidth of 10 megabits per second, okay? It can pass an average of 1,200 frames, 12,000 frames per minute, right? Each frame carries about 10,000 bits. Can you tell me what the throughput of the system is? On your own, I want you guys to sort of work through this and tell me how you compute this. Take a minute or 2 on this. So bandwidth is the limitation of the network, right? You're doing 12,000 frames per minute, right? And each frame carries 10,000 bits. What is the throughput of this system? Anyone want to share how they would approach this problem? You don't have to give me the numbers. You just have to show me how you approach it. Rana, are you still there?
Yes, I'm here.
Okay. What would be your approach to solve this? How do you determine the throughput? Remember, the throughput is what you actually use, right?
Well, it's per minute, and
That's
I need
right.
it to be per second.
That's
so
right.
I can actually.
Exactly. So essentially, that's what why you compute, right? You have 12,000 frames. Each frame carries 10,000 bits, but because you want it to be per second, right, divided by 60, which means, right, your actual throughput of the system is strictly just 2 megabits per second, right? And you can use this network because this network can support up to 10 megabits per second. Okay, so that's an example of the computation of throughput. Let's take a look at the more interesting propagation and transmission time. Okay, so I want to know what the propagation time is and the transmission time is for a message that's 2.5 kilobytes, right? If the bandwidth of the network is 1 gigabits per second, and obviously now because I want propagation time, that's the distance. It's 12,000 kilometers, right? And the propagation speed of light, right, is at 2.4 times 10 to 8 meters per second. Can you compute what the corresponding propagation time is and transmission time is, right? Obviously, right, I've given you the formulas to do so, right? This is propagation time. This is transmission time. And and share with me, right, what you think, right, is the more dominant time in this case on your own, right? Take 1 or 2 minutes to sort of look through this problem. How do you compute propagation time? How do you compute the transmission time? Shankai says, right, propagation time is distance, right? Obviously, okay? So that's what we have, right? We need to figure out the total because we want it to be in meters per second, right? Because this is given to us in meters per second. So we need to convert this 12,000 kilometers to meters, okay? And obviously that will be the propagation time, right? Because the distance divided by the speed. Okay? The transmission time, on the other hand, right, is the file size. And capital B just means bytes, right? 2 kilobytes, 2.5 kilobytes, right? And the transmission speed, right, obviously, right, in terms of bandwidth with the network is 1 gigabits per second. So you have 2,500, which is 2.5 kilo times 8, divided by 1 times 10 to the 9. So in this particular case, right, you'll see very clearly. In fact, the propagation time, right, is dominant. Does everybody see that? Why? Because it's a relatively very small file, right? You're transmitting a 2.5 kilobyte file over a 1 gigabits per second network. It's almost instantaneous, right? It takes 0.02 of a millisecond to transmit that. But in this case, right, the dominant delay actually is incurred because you're transmitting this very small file size across a distance that is very large, right? Which is 12,000 kilometers in this case. Well, it is still very fast because it travels at the speed of light, right? But it's 50 milliseconds. Comparatively, though, right, to 0.2 of milliseconds, right, the propagation time is dominant. Okay? Any questions? So if there are no questions, right, a couple things that you should know of, right? So that you have a quiz next week, okay? And then the quiz will cover all the way through to section 3.6, with the exception of 3.4 and 3.5. So there'll be no questions on 3.4 and no questions on 3.5, but you're responsible to work through all the way through to 3.6. In addition, you should make every attempt to work on the assignment, right? Assignment 1, so that you can ask questions, right, during the class prior to that. And then Rana, I did not get time to go through the solutions to the quizzes from last week, but I'll do so next week. Just remind me that again. Okay, Rana?
We'll do that. Thank you.
Yeah, sorry about it. It's just because of the time-wise, I didn't get to do that, but I'll do that next week.
No worries. Yeah.
Okay. So if there are no other questions, right, this sort of concludes the class for today, right? We will regroup again next week on 9 o'clock on Saturday, right? Any questions, please send me an email. But please work on the 2 things that I ask you, right? 1, to study for your quiz, keep up with the material, right? We'll cover through all the way through 3.6 with the exception of 3.4 and 3.5. Okay, so I'll stay online for a few more minutes if you have no other questions, right? But if not, you can log off, right? And please have a great long weekend, right? Whatever that means. And please, right, try to abide by all social distancing rules, even as we enter phase 2, right, in BC. Okay, so everybody please stay safe, right? And I'll see you guys next week. And I'll stay on for a few more minutes if you have questions, but otherwise you can log off and enjoy your weekend. Okay, thank you, everybody.
Thank you. See you next week.